Hey, can everybody hear me?
I can.
I do.
Okay. Sorry, I had problems with my audio previously. Okay, thanks.
Hi, cool kids.
Hey, how you doing?
I'm okay. I presume to do the cool kids hangout because that's what I'm trying to be. Obviously, join with them.
I will tell you later.
So the M on your hat, I'm sure isn't that, but it reminds me of Monsters Inc. A friend of ours, their daughter is named Boo. Her official name is Charlotte, although she's actually on her birth registration, I think, as Boo as well, certainly christened Boo as well. And the reason they called her Boo was because they had an elder son who was kind of 4 or 5, I think, at the time, and was very anti having a baby sister. But really enjoyed Monsters Inc. And the girl in that is called Boo. And so they referred to her before she was born as Boo. And it kind of stuck when she was born. So she's known to one and all as Boo. She's now sort of 15, 16, and nearly 17. And yeah, is Boo to everybody, which is quite fun. So random story of the day.
Very nice one, though.
So give it another minute for people to join. Any other extra topics people want to discuss today? We have a list here. The main topic is going to be Stefan from IBM presentation.
I will drop that link into the Zoom chat here. Oops.
Okay, I see Stefan is here. So I think we can go ahead and get started. If there's no opens, we'll go ahead and Stefan, if you want to go ahead and share your presentation.
Yes, I can do that. You hear me, right?
Yeah, can hear you.
Hey.
I just have to find the button and hopefully share the right image, but no, it's the wrong, right? New share there. And now you should see my presentation, right?
Yeah.
Okay, thank you. So in February, I was in FOSDEM and met Thomas Fossiati, and we talked about attestation and confidential computing in the whole. And I noticed, or we noticed, that you know not so much about confidential computing on the S390 architecture, and especially attestation. So he asked me to do a presentation about it, especially about attestation, but also about our confidential computing implementation. It's called Secure Execution for Linux. So just introduce myself a bit. I'm Steffen Eiden. I work for IBM as a software engineer for Linux on IBM Z, and mainly do secure execution development. So today's agenda is I give a brief introduction into secure execution, and then talk a bit about explicit or remote attestation.
Stefan, are you happy to take questions as we go through, or would you prefer to
Yes,
wait to the
you
end?
can ask questions, but and I will additionally give you at the end of each section few
Thank you.
space for more questions, of course. So let's start with IBM Secure Execution for Linux. It's a technology that provides you to run your confidential workloads securely in a public, private, or hybrid cloud. So the goal is, as for any confidential computing solution, is to protect the data in use against malicious hypervisors. As for the hardware requirement, you will need an IBM Z15 or CCC16 or the respective Linux One machines that are, from a hardware perspective, the same machine, but you can only run Linux on it and no proprietary OS from IBM. It will not protect you from any network or attacks, but it will prevent you from attacks from the host. And with network encryption and disk encryption, we have a fully encrypted system. So our threat model is that secure execution prevents your guests, your secure execution guests, from being accessed by the host, and the host cannot modify the guest state of the secure guests. It will not prevent you from denial of service attacks from the host or bugs in your own software. With some features with C15, we implemented basic secure execution. Will allow you to have an encrypted guest image, and we also provide you that the host can swap and over provision memory. With Z16, we also added the remote attestation, also hypervisor initiated dumping of the guest without leaking any secrets, of course. And in 2024, just now, we also provided implementations for secret store in the trusted computing base and also crypto pass-through for crypto adapter cards. It's available in all KVM and QEMU distributions upstream for guest and host. We are currently working on enabling it in confidential containers and also other server platforms. So let me start with the general architecture of a Linux One system or IBM Z. And as for every architecture, we have, yeah.
Excuse me, Sam. Yeah, can I ask a quick question?
Yeah, of course.
So the protected environment sounds like a virtual machine.
Yes.
What sort of measurements are available for remote attestation as to what software is running in that virtual machine?
I think I will answer in my presentation later on.
Okay, great, thanks.
If not, then just ask me after my attestation part.
All right.
Okay, so as for any other architecture, we have some hardware, in our case, the Linux One or IBM Z hardware. And as part of the firmware, there is a hypervisor. It's called Prism. It stands for Processor, Resource, and System Manager. Is a bare metal hypervisor, and allows physical separation between virtual machines. And we often call it guest zero. And on top of that hypervisor, you can run your quote-unquote bare metal operating systems, for example, the IBM proprietary systems, operating systems, the OS, CVM, and also, of course, the Linux. And what's mainly important for us now, ZLinux plus KVM. And this layer is mostly called guest 1. And it's more or less the quote-unquote bare metal operating system. And of course, we can run KVM guests in our ZLinux. Mostly they call them guest 2, 3, 4, 5, and as high as you want to go. And you can run normal KVM guests and also secure execution guests. And secure execution guests are only available at guest 2 layer.
So may I ask a question? You may be getting to it. I remember previous iterations of this architecture. I think what I'm seeing here, but I'm not sure I'm correct, is that the actual execution isn't protected by hardware, but the root of trust of the Prism is based in hardware. Is that correct? So the actual protection of the memory pages is not performed by hardware. It's performed by the hypervisor in guest 0, which has a root of trust in hardware. Is that correct?
That is correct. Yeah, we
Okay.
We ensure that the hypervisor, so the guest 1, has no access to the guest memory and CPU data.
But that protection is not performed by hardware. That is just a check that the Prism is the expected software. Is that correct?
I'm not sure, to be honest, which part really does the separation, but the hardware and the firmware together ensure that the memory is protected. And this thing is, we also mostly call it ultravisor because it's has a more secure level than the hypervisor, and it's also part of the guest 0.
Okay, so let me try rephrasing the question.
Yeah.
Then. Is the ultravisor performing the isolation, or is the hardware performing the isolation?
The ultravisor is ensuring that the guest 0 cannot access any pages. That's
okay. Yeah. So it's the ultravisor. So that's in software, not in hardware.
That is CPU firmware.
Oh, CPU firmware. Okay. So I think this has changed somewhat from when I last looked at the architectures about 5 years ago, and I think then we probably would have said that this wouldn't have met the definition of confidential computing, which is protection by hardware-based TEs. But I'm wondering whether now it does, if the actual protection is performed by the firmware and the hardware, rather than it just being basically a trusted chain of software. And is that fair?
Yes. Yeah, I think so. Yeah.
Okay. Let's carry on. Let's carry on. And if other people have other questions, that's really helpful. Thank you.
So yeah, but in fact, we have a CPU instructions. I will come to that. That's called the ultravisor call instruction, and that's used for managing the secure guests.
That is very helpful as well.
Yeah. So I will have some more concepts for secure execution that are important to understand the attestation. So I assume there are no more questions, or are there? Okay. As I just told you before, we have our hypervisor or KVM that's not part of the trusted. The IBM Z firmware or the ultravisor ensures that the hypervisor cannot access guest memory unless the guest explicitly shares that memory to the hypervisor. And also the guest operating system is encrypted with a encryption key that's handled by, or that's protected by the client private key and the host public key. And the ultravisor will encrypt the image later with its own machine private key that's only available in hardware and will never leave hardware or never came from outside. And the hardware and firmware ensure that the unencrypted machine, so that no unencrypted machine state, for example, memory and CPU state, will ever be accessed by the host and the hypervisor, or the administrator of the host machine. It's also protecting from these persons. The KVM is still responsible for the actual I/O and the housekeeping and scheduling and memory management, but without accessing the unencrypted memory ever. The host public key is signed with our IBM signing key. And this signing key is also signed by an intermediate CA. Currently, it's we're using DigiCert for signing our signing keys. So that's a chain of trust, and so you can prove that you're really using a IBM certified signing key and not any key from any middle you probably don't want to trust. Okay, so for running a secure execution guest, we need a secure execution image, and this has some protected components. It's mainly the kernel parameters, and the initial RAM file system. All these components are encrypted beforehand and also measured during the image preparation. And the ultravisor on boot of the secure guest will verify the components against the measurements and will only start the image if those measurements found to be valid. So as our init RAMFS of those guests are encrypted, we can store secrets there, for example, an SSH key or our disk encryption key.
Quick
Yeah.
question, if I may. What's the definition of be valid?
So there are hashes of the memory of the yeah.
I think I understand at a high level that the image is encrypted and hashes can be calculated over the image, encrypted or decrypted. And there's some loader that's loading, that's decrypting and loading. I don't understand the policy that's applied before it says, okay, I'm going to launch it, which I think is what you call be valid.
Yeah, so it's AES.
It could be as simple as well-formed or something more like some sort of policy, right?
It will ensure that no attacker tampered with the image. Using AES GCM stuff. And
so when you say no attackers but you need to have a reference value, and presumably you need to decide how to trust that reference value. So is that in a whitelist? Is it signed? How's that working?
Yeah. So during encryption of the image or of the components, we calculate hashes of the pages and of the addresses where they are, and a third one I just forgot. And these hashes are stored in our secure execution header, and these hashes are protected by the header AES GCM tag. And if the ultravisor found those hashes to be different than the one he calculated just during the boot, it will reject the booting.
And how are those hashes communicated to the ultravisor?
It's a part of the secure execution header, and that's just it's architected binary blob that contains those hashes, and also these hashes.
I think what this is saying is that it's ensuring that the image hasn't been tampered with. It's consistent, it's well formed, but it's like from a trust decision perspective, like, is this a trusted image that was created by Coca-Cola? Nothing like that's happening. I think that's what I'm hearing.
Yes, yeah. It's just ensuring that the image itself was not tampered with and not by whom, or not created by whom. We don't care as of now.
So no provenance decisions here. It's just about integrity.
Yeah.
And the decryption key is stored on that platform?
Yeah, it's part of the we go there. It's part of the private key, so we use is part of the machine hardware.
Okay, so you're going to encrypt an image to a specific platform.
Yeah. Okay, and you can do it for multiple concurrently, but yeah.
So, Stefan, you should be aware that this is a group who likes to ask lots of questions. This doesn't mean these are negative questions. They just like to have a deep understanding.
Yeah, it's completely okay. Yeah.
And I think one thing to say to the folks is that you have to think not cloud here. This is not a standard cloud model of how you might provision machines. It's a very different one, and I think designed to work with that rather than sort of a hugely distributed, lots of different images. These are very well tailored images for particular hosts and stuff, right? Is that fair, Stefan?
Yes. So, but you can prepare one image for multiple host machines, but yeah. So typically customers don't have so many machines they want to run their workloads on. So because as I did before, we can run many OS on one hardware platform, and so many different hypervisors and many millions of guests at one platform. So there are not so many different hardware machines in one location for most. So it's not like you have like 400 different hardware machines in one location. That's very unlikely.
Yeah, because I mean, these machines cost several $1 million each, right? We're not talking sort of a couple of thousand each.
Yes, it's not a couple of thousand, of course, yeah, per machine.
This is a big mainframe.
Yeah. Okay. Any more? Okay, so I will just go through the life cycle of those guests, just for reference, more or less. So when the hypervisor boots, it will donate some memory to the IBM Z firmware, to the ultravisor, so it can use its housekeeping. And of course, hypervisor cannot access this memory after the donation. And then the hypervisor will start, or when the guest owner asks the hypervisor owner to start the image, just as a normal guest, unencrypted. And if you prepare your guests with our tooling, it's more or less just a bootloader to do the next step. And the next step is that the guest asks the hypervisor to transition into secure mode. And then the hypervisor will trigger this process. It's mostly done via the ultravisor call instruction. And at this point, the ultravisor decrypts the image and verifies the integrity. And if it was performed successfully, the hypervisor can then ask the ultravisor to start the secure execution VM execution, and will execute the image. And voila, you have a secure execution encrypted protected image.
Okay, so when you trigger this transition process.
Yeah.
How is that isolation being performed? Is all those memory pages encrypted? Are there other types of isolation to stop access? What's the actual mechanism by which that happens?
So yeah, the secure execution image itself is encrypted. That was prepared somewhere else.
Yep. Got that.
At your trustable machine.
Yep.
You trust. And then the hypervisor will give the firmware an address where it can find the image.
Yep.
And the image includes also a header. And there's some more information and we have those our measurements for verifying the integrity. It's part of the secure execution header. And the hypervisor points to the encrypted guest memory.
So the encrypted guest memory is set up by what? By the firmware?
That is part. So the decryption is part of the firmware. Yes.
So, and that memory is what was donated by the host OS.
That is part of that's part of the guest image. So that's so we were kind of a guest context here, but in the hypervisor. But to be really honest, I'm not so firm into this whole things because I didn't do that. So
Fair enough. We should.
yeah.
I think we'd love to talk to someone about that as well. Let's move on to the attestation side. Thank you.
Because
Sorry.
that's the part I did. Yeah.
Absolutely.
But yeah, that's mostly the also simplified life cycle. Yeah. But yeah. Maybe I can point to some documentation afterwards. So let's start with the attestation part. So for verifying the integrity of the image, secure execution does not require external or remote attestation to prove that the image is a valid one. And especially if your image contains a unique SSH key, so a unique public SSH key, a successful login would implicitly attest your secure execution image. That is a valid secure execution image and it is yours. But there are use cases for explicit or remote attestation is, for example, you may want to prove to a third party that you're using a secure execution or your image is secure without giving them your SSH key. And also you may have multiple secure execution running guests at the same time, and you will want to verify that you really have multiple guests and you want to differ them between in a secure way. So for the remote attestation, you create an attestation request on a different secure machine you trust. It can be your own laptop, for example, or another secure execution guest that has been attested before. The main payload of that is the symmetric attestation measurement key. It's encrypted in the attestation request, and it's just a HMAC SHA-512 key. And similar to the secure execution header, it's also derived using or encrypted with the host public key and later on decrypted with the host private key. That this attestation request got sent to the secure execution guest you want to test, and the secure execution guest sends it to IBM Z firmware, or the ultravisor. It will measure and do some measurements, and that's an HMAC, and it's over the hashes, over the hash of the kernel parameters in interrumfs or the memory. And that's one hash, and also the tag of the SE header and a unique ID of the guest. It changes. That's unique for each secure execution guest on the platform, and also some additional optional data. For example, in this case, the hash of the public host key of that machine you're currently running your attestation. So as you could prepare also the attestation request or your image for multiple hardware platforms, you could then differ or decide on which or see on which hardware you're really running on. And then this result gets sent back to your trust machine, and then you can verify the result. How I will do later or with the next slide. So
that key derivation, is that just ephemeral to that session, or is it somehow deterministic and persistent across sessions?
So the measurement. Oh, sorry, I didn't understand the first
Sorry,
part.
the symmetric encryption key that you're sending encrypted in the attestation request.
Yeah.
Is that ephemeral to that session, or I'm not sure what the key derivation implies.
Yeah. So that's just a random key you generate during the attestation request generation.
Okay.
It can be anything. Yeah. So go a bit deeper on or more details on the process. So the attestation or the verifier, I think it's called in the COCO environment, is creating the request that contains a symmetric attestation measurement key, and if you want an optional nonce. But that nonce is just to ensure that you don't encrypt same data twice. And it's also encrypted. the verifier or the attester sends that request to the secure execution guest, and the secure guest, as just before, to the firmware. The firmware will measure it, send it back to the secure execution guest. The guest sends the measurement, and also with our tooling, at least including the request, back to the verifier. And the verifier will then recalculate the HMAC or the measurement. And if they, and compare them to the one he received from the secure execution guest. And if they match or they're the same, the attestation is successful. And if they are different, the attestation failed. Okay. So let's, the last slide about attestation is a bit more on the guest
Sorry,
side.
quick question. If it fails, what are your options?
So there are, so if it fails, there could be multiple reasons. For example, you missed some, part of the measurement is guest data, that's part of the guest image. So maybe you selected the wrong image to compare with. So then the measurement would be not.
So what I meant
matching.
was, if it does fail, what can you do with that information?
Okay, so you know that if you're sure you're inputting the correct data, that someone tampered with the measurements. Or
yep. So
you
what
cannot
do
be
I
sure.
do now?
Yeah.
Yep.
What do you do now? So maybe send another attestation request, but or double check that you're using the correct data. Yeah.
Do I have any options to contact the ultravisor and say this is untrusted and you should close it, or do I just have to decide not to continue with it?
Not continue with it and do and shut down your guest probably.
Okay, and I have the opportunity to do that. Okay,
yeah,
that's fine.
Yeah.
Just trying to understand. Okay, that's good.
Yeah, if it's a malicious guest and just pretending to be a secure execution, it can do whatever it wants, of course, but yeah, or what the hypervisor wants, but yeah. So when the attestation request is sent to the guest, it's of course in user space, and as the instruction we use later to perform the attestation request or to send the one to firmware, it's a privilege instruction. We need to swap to kernel space. There is a device I developed for that's under /dev/uv on S390 only, of course, and that's called the ultravisor device, and it will handle like the real firmware instruction. And at this point, the secure execution guest can also inject some local or user data. That can be anything you want. The idea behind it was to add some hashes of your disks or your root file system or whatsoever that's encrypted with your LUKS key, and that can be evaluated after the attestation was succeeded, because we only assume that this local data, so this local data will be part of the measurement, is as inputted as it was here in this case, in here. Nothing, everything else you have to check on yourself. So the ultravisor device or the driver will do the ultravisor call. It's an S390 extraction and has a control block. We are a very CCC platform, so yeah, we can do everything. So access memory for any instruction is possible. So just a part of the memory is that, and it contains the user data, the request, and also prepares the memory to be filled for the return data for the ultravisor. The ultravisor will then do the measurement and write in the unique ID and also some more, for example, the hash of its public key. And then the way goes back from the kernel space to user space, and the secure execution guest sends the data back to the verifier. Okay, and that's mostly it for the attestation part. I have just one last slide with our feature metrics. If you want to try it out and have a machine by hand. Yeah. Also for the tooling part, so generating attestation requests and so on, you can also use on your own machine, on your laptop. If you install the S390 tools or the S390 utils on RHEL, and try it out yourself if you want. But you only can create the requests and not performing them because you would need hardware. And also, I think I should upload the slides anyway, so also some more information on the documentation and some more presentations that shed light on different things. So thank you for this, and I'm happy to answer all your questions.
Cool. So we love talking about the nuances of formats and trying to make sure that wherever possible, we're all getting onto the same standards.
Yeah.
Can you talk about anything with the data formats that you use in the actual attestation messages?
So you probably mean those here, and
I mean, in particular, if I want to
Yeah.
go verify an attestation that I've received,
Yeah.
what kind of data am I handling?
so you need so if you're the verifier, we go back to the verifier. You will need, of course, the measurement, of course, and the header of your secure execution guest, or more precise, the hashes in that, but we provide tooling to extract that. And if the guest adds some local data, you will need the local data as well. And if you requested in your attestation request to add some additional data, that data as well. But that's part of the answer anyway. So
Mm-hmm. Okay. Yeah, maybe in
so for
like a,
yeah. So
go ahead.
I'm not sure if you're talking about the COCO part or whatsoever, or it's just a general one. But yeah, we are investing also in the COCO's implementation, and also
it might be a different presentation, but the like the formats that I'm referring to would be like encodings and things like that. So, you know, you're packaging these things up in JSON or CBOR, they're using EAT tokens. This sort of like standards soup is a topic that we like to get into, which is totally fine if you don't have that for today, but that would be interesting to this audience in the future.
I'm getting a lot of Slack messages right now. Maybe one of my colleagues is sending, but I have to unfortunately stop screen sharing for this. So you don't see my screen right now, right? Okay.
No, I still see it.
Oh, you,
okay, it's gone.
Yeah. Is it?
I do have a question in terms of the flows.
Yeah.
When the request is made to the workload, you need to know the public key of that host in order to initiate.
So if you you need the public host key, but that's provided by IBM, and you could verify it always. That is genuine.
Okay, so it doesn't start with the workload requesting access to some secret where it generates a request and then is challenged, where that request contains the public key, or
so we provide publicly the host key documents. So you more or less have to input your machine serial number, and then it will get the host key. But and then the tooling, or you could do it yourself, issuing OpenSSL commands, will verify that this host public key is genuine. And then the tooling starts generating the attestation requests using that public key. Or you could do it yourself as well. Write your own tool.
so it's more of a push, like a provisioning flow, where you want to provide a secret to that platform, and it's the secret holder that initiates the flow.
Yes.
Okay.
Yeah. So the verifier needs to initiate the flow or get some hint to start that.
So if I'm thinking about the end results of that attestation, where the results are produced and given back to the party that initiated that conversation, does that attestation evidence on its own, is it complete if to verify? So there seems to be, I mean, typically with this kind of attestation evidence, like an entire certificate chain tracking back to like a root of trust for a hardware vendor is part of that attestation evidence. And it sounds like I'm guessing here, but based on what I'm hearing is up front, this provisioning step, you get essentially attestation evidence from the hardware vendor, basically saying this is a trusted key for one of my hardware devices. And then you send that off to that hardware device and ask for the rest of the attestation evidence. But you have to, if you're just thinking about someone auditing, another party auditing, or looking at this in the future, and if you need all the pieces to kind of verify trust, it seems like two pieces are required: that what you got in that initial provisioning flow, and then what was returned when that attestation was requested. Is that true?
So
or?
The host public key is only used to ensure a secret channel between the attester and the IBM Z firmware or the ultravisor.
But it's also used to establish trust. I mean, you just don't go to any random host key. If they talk the protocol, you say, cool, this is an IBM machine, and I can trust that, there's hardware enforcing these things, right? There's a trust decision saying, what's at the other side, what owns this host key is IBM hardware, which has these security characteristics. So I just don't trust. So that's part of, like, if I get this attestation evidence in the future, signed by some key, I don't know anything about how trustable that stuff is, unless I can track the key that signed it to some particular, security characteristic, but like to some hardware vendor with some sort of secure execution environment.
Yes, but so yes, you have to trust IBM that we do not share the private key. Yeah, and also the X509 root of chain of trust architecture. Yes.
Yeah, I think all I'm trying to confirm is just a data structure. It's just a data structure question. I think for what I'm the full body of information I'm envisioning some party at some point wants to have to ask and answer the question, what were the measured characteristics of this environment, and do I trust it? I required two pieces of information. One was the result of this conversation, which is with the host, and the other is this guessing an X509 cert chain that shows that this is a key. This host key is changed to IBM.
Yeah.
Okay.
Yes.
Thank you.
Yeah. So yeah, of course, if you have a random public key and that's not certified, anyone can sell you anything.
Yeah. It just yeah. Okay. Thank you.
Yeah. You're welcome.
Just a quick follow-up on what Greg said, and sorry I joined late. I missed some parts of your presentation. Isn't it true for all the TEs that you need to trust that the key is not leaked? I mean, I don't see it as any different from Intel, where we have to trust that the Intel's key is never leaked. Like any certificate in the chain is not compromised. So what difference do you see? What Greg was mentioning, I didn't follow that. How is it different from any other TE? Isn't it true for like all TEs that you have to trust that the key is not leaked? The certificate chain is correct. So how different is it from others?
So I have not so much information about the other TEs, so I'm afraid I cannot answer that.
I think he's asking the original questioner, not you, Stefan.
Okay. Yeah. Okay.
So who asked the question before about whether?
Greg, I think it was Greg. So Greg, do you have any thoughts on that? So
no, I think that from my perspective, it's just a data structure question, right? As a, the part of the puzzle I work on is a verification service, and so I am consuming attestation evidence produced in an environment, and I need to evaluate it. Is it trustable? And then end up creating some sort of token with some sort of claims that are useful for a relying party. And so I'm envisioning every other, in order to make that first decision, like, is this attestation evidence trustable? I have to chain it back to some sort of root of trust, typically a hardware vendor's root of trust, the Intel root CA or the AMD root CA. And if the if the data in this attestation evidence ultimately is signed and traces back to that CA, then I can move on with kind of the verification logic and the verifier.
Right.
And so as I looked at that diagram, it seemed like that the pieces I need for, like, if a verification service like MAA is going to verify this evidence, I need the measurements that come out at the end, and I also need this certificate chain showing that this machine key is trusted, that ultimately I think signed that evidence, I imagine. And so I was strictly asking just kind of a data structure question, and this goes back to the earlier question was in terms of, we thought a lot of time, we were interested in talk about standards and interop and consistency in this group. And what's behind that question is, my question is not only just coding or being on a team that runs a verification service, is also thinking in terms of consistency and standards. The structure I've seen is that this kind of comes as a complete complete package, right? It's not thought of as disjoint. They're packaged together. So that's I didn't see the model as different. Just the information is not naturally, from what I can tell, put together kind of in the flow. If you want it, you have to get it from two different places in the flow.
Right, I get it now. So basically what you're saying is that the flow and the key hierarchy and everything, like certificate chain, everything is similar, but the difference is that you're thinking more from the data structure perspective, and the more the interoperability part, how this evidence format would fit together if you want to design an verifier which takes, let's say, in addition to Intel, ARM, AMD, and so on, blah blah blah. Also, it takes IBM as an input and then generates some. Okay, right.
Or maybe another way to think of it is, if you imagine a relying party that's going to, so the flow that was presented is the relying party is doing the request for attestation evidence. So I think it's the background check model. If you imagine a flow where it's the passport model, then the passport model, there's one piece of information, the passport, that's given to the relying party that has to include everything that's required to establish trust in the measurements plus the measurements. So the flow here works for background check model, where the relying party says, I want to know what's in this environment and do I trust it. So I'm going to do two steps. I'm going to discover a trusted machine. It has this key. Then I'm going to go to that machine and then discover trusted measurements signed by that machine key. That works for background check, but doesn't work for passport model. And I guess MAA is a verification service. We support inputs that are essentially passports.
So MMA supports only passport, is it what you said?
That is. I have to think about it a little more, but at the moment, that's ringing consistent. That's what makes sense.
Okay, right.
I thought you can get a token from MAA and then you go around showing that.
You can, but MAA never actually. MAA is not in the current flows. MAA is not involved in querying the attested environment. We don't, let's say, for example, like Verizon, I think, can generate a nonce that then gets fed into the attested environment, and then the attestation evidence that comes back reflects that nonce. That's not how MAA works at the moment, right? The existing APIs we have in there. It's, all of the attestation evidence is harvested external to MAA, then handed to us. That's such, like a passport would be. And so if there's a nonce kind of conversation at the moment, that's basically a contract between the relying party. The relying party would have to go and and request that attestation evidence, put the nonce in, get the flow through MAA, then check the nonce value in the resultant MAA JWT. That's the current way, the current structure of the APIs.
Okay, I have one more question. I'm not sure if you already covered in the slides or not. So this is a question for the speaker. So in your tool chain or the frameworks that build around this attestation service that you have for IBM, what kind of secure channel establishment is used, like techniques for secure channel establishment? Is it the integration with the TLS protocol, or is there some other protocol, and how does it work? Can you clarify a little bit?
Yes. Let me check the slide. Okay, we are here on the correct slide. So more or less, we use a very similar to TLS scheme. We encrypt the guest image or the attestation request with a symmetric key, and that symmetric key is derived using a client private key and the host public key, and then in the other way decrypted using the machine private key and the client public key.
But does it work like so? How is the channel? I mean, has it something to do with TLS or not?
It's
like the client
no,
hello, server hello. So these kind of messages, are
No,
they not used at all?
No. There is a one way. It's the client will encrypt in the secure execution image or the attestation request. They are very similar. And when it's encrypted, it will send to your hypervisor, and the hypervisor will start the image, and then the image is verified. But there's no like handshake and for back and forth.
Okay, so
the only thing that could be go into that area is if you see the whole concept, start the image and then attest it, and that could be seen a bit like, but yeah.
Right. So you do not have any transport protocol, so to say. So
No.
it's just encryption and decryption, and that's it.
Yeah.
Okay, right. Thanks.
Just one more question about the firmware itself. So if the firmware is found to have a vulnerability, does the firmware support a TCP recovery mechanism where you can update the firmware and reattest its measurements? And are those reference values published? For example, like a security version number or some other type of hash that indicates this is the most up-to-date version of the firmware. In DICE parlance, it'd be like the alias key. Does the firmware produce an alias key based on the device key?
I'm not completely sure about everything, but I know quite sure that currently, as there are multiple firmwares with multiple versions and multiple subversions, there's no like this one firmware version at one time. But we provide firmware, yes, in bundles, and you know in which bundle version you are.
Okay. Yeah. I guess the question is the firmware itself attestable?
Yes. So
okay.
By IBM, yeah.
Okay. Right.
Yeah, and I will share these slides afterwards. Yes.
Thanks. Any other questions? Got 7 minutes left. All right. Thanks,
so if I have to, sorry, just a quick question. So if I have to think about how to go about formalization of this whole thing that's involved in the IBM remote attestation, so is there any work towards that already within IBM, outside IBM, some open source, or is there already a plan for that, or can you say a little bit towards that? So what's the state of the formalization for specifically for this attestation side?
Okay. So as of the kernel stuff, everything is upstream. And we also provide tooling that
Sorry, no, Stefan,
or-
sorry.
or-
I think Osama's interested in formal proofs of and formal verification of the protocol.
Yeah, exactly. So
Yeah.
maybe just to clarify more, like creating a model, doing like a formal model, writing some properties in a formal language, and then verifying some properties. So this kind of, are you aware of any effort within IBM or outside IBM towards this,
I'm not
specifically
aware
for
of, no.
attestation?
No, I'm not aware of.
Okay, right. And if one has to start about this thing, so what would you think about, what would be the most valuable thing to start with, or what do you think would be the starting point for this?
So I'm not so confident with those formal verification things. So
It's okay.
unfortunately,
It's okay. Yeah,
I
that's
don't know.
fine. No problem. Yeah, thanks.
You're mute, Mike.
Are there members of your team who Osama could maybe speak to, or folks within IBM who do know, who are interested in this sort of stuff? You know?
Yeah, I know Reinhard Bündgen. He's the secure architect. I don't know if you have any minute notes, so I could add that to those. Or
There are minute notes. If you look in the chat, you'll find them there. The other thing is, I think it'd be really interesting to have a presentation, maybe to the full TAC rather than to the attestation group, around the architecture of the actual execution. And the stuff that, this has been on the attestation, which has been really, really interesting. But I think the TAC, the bit wider TAC, would be really interested in that. So thank you to Stefan and all of the IBM folks for turning up. I know that Rachel had to leave, but this is really, really good to have everyone. Thank you.
Yeah,
okay, I will bring that up. Yeah, you're welcome.
Okay, we have 4 minutes left. The other topic was for the issue 13. This had to do with the formal verification on the KBS attestation protocol. I'm in the process of reviewing. There are some other discussions there, so if you want to take a look at that. Usama, you're still here. One question I had was, I saw in there the ability for the well, it does have a comment saying that the verifier can specify the evidence format that the tester should use to generate the response to the challenge. But I didn't see anywhere in the spec where that could be listed. Like, what are the supported formats for the verifier to allow the TEE to generate that format? Is that included in the protocol?
If I understand your question correctly, you are asking about what protocol formats or whether protocol formats, the evidence formats will be included in the formal model or not. Is that correct?
Yeah. For example, if a TEE could support more than one evidence format, is there a way for that information to be communicated to the a tester prior to generating the evidence, versus having to wait for an error to go through a list of ones that pass?
Okay, so at the level of abstraction that I verify, I think the evidence, what we really need to see is what kind of cryptographic information is there in the evidence, and it wouldn't matter a lot if there is, let's say, one field is before or after, or the other way around. So that's just to say that the most important information that we would capture is the cryptographic information, what is signed, what exactly is signed, and for signing it's important that, okay, in which order they are signed, hashing which order they are hashed. So we I think I wrote in the also in one of the motivations that the reason of selection of this was that it supports already a lot of T's and Intel ARM, AMD, and so on. So it's one thing that we would capture and try to connect it to our previous artifacts, at least with ARM and Intel TDX. We will try to verify. So at least we will have two different evidence formats. But just to clarify, it would be at an abstract level a little bit. So it would not be, let's say, one-to-one match between each and everything. So it would be a little bit abstract. So as a sample, you can see our artifacts from the other project where we have for Intel TDX and CCA. I think I have a link also to within the issue. I have a link to other works also which were carried out. Does
Okay,
that clarify?
I think so. Well, what I'll do is I'll put the question in the issue itself, and maybe that'll help.
Yeah, sure. I will be
with the
happy
top
to
of the
yeah.
we're out of time. Before we leave, some clerical. Don't know who else is here. I know Greg is the other chair.
I can take next time. You can just
Okay,
put me down unless somebody else is itching to volunteer, but I don't even see anybody else.
Like that
on
ever
this.
happens.
Yeah.
It's like
and I've confirmed this morning that one of my colleagues is still looking like he'll have his talk ready for 2 weeks from now on how we do confidential container policy inside of Azure and some what we think are some cool features of what it enables. So that looks on track.
Okay, great. All right, everybody, out of time. Thanks for joining.
Thanks, everyone. Bye.
Thank you.
Thanks.
Bye.
Thanks all. Take care.
Bye.